Hello, everyone. Welcome to today's webinar. I'm Catherine Dold with CNEN, and I'll be moderating today's event. This webinar is titled Introduction to Gas Chromatography Method Development and is being sponsored by MacMod Analytical Incorporated. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with their mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look for the Help widget at the bottom of your screen or type your query into the Q&A box. If you get disconnected during the webinar, please log back in according to the instructions you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. Our speakers will answer them at the end of the presentation. As your moderator, I'll be posing as many as time permits. Please note that CNEN does not endorse any company products or services that may be mentioned in the webinars, and that each webinar will be archived at CNEN online after the live webcast. Our presentation today is being sponsored by MacMod Analytical. MacMod says, a company should be able to condense its mission statement into a simple phrase. MacMod's mission statement is smarter chromatography. But you may ask, just what does smarter chromatography mean? It means that when we make a recommendation to you about an HPLC or UHPLC product, it is to partner with you to offer innovative solutions to your complex problems. We used advanced state-of-the-art analytical software to match our product portfolio with your separation needs. We leverage our 30 years of experience in the LC column business, our technical expertise, and our manufacturing network to help you solve your toughest application problems. We provide up-to-date and accurate technical catalogs and reports from industry-leading separation scientists to keep you informed of new technologies. Our speakers today are Kirsty Ford and Tony Edge, both from Avantor Incorporated. Kirsty Ford is a senior chromatography technical specialist at Avantor Sciences, part of the technical team supporting colleagues, distributors, and customers worldwide on a range of chromatographic products, including GC and HPLC columns. With experience as a remote support engineer with Agilent Technologies, focusing on GC and GCMS, they bring a wealth of knowledge in chromatography, troubleshooting, and product insight. Tony Edge is site lead at Avantor Sciences, leading a team of specialist scientists in manufacturing and developing next-generation stationary phases for HPLC. He has worked in both manufacturing and in industry, having periods of employment at LGC, AstraZeneca, Thermo Fisher Scientific, and Agilent Technologies. In 2008, he was fortunate enough to be awarded the Desti Memorial Lecture for his contributions to innovating separation science, and in the same year also won a Clinical Excellence Award from AstraZeneca. I'll now hand the program over to our speakers.
Hi everyone, this is Kirsty and we're going to go through the agenda. So we're going to go through establishing objectives, tools and selectivity in GC development. We're going to have a look at goals of optimizing the GC parameters, standard GC method development with split and splitless injections, and then we're going to go on to fast GC with method transfer guidance. So where to start with GC method development? We want to establish objectives, tools, and the selectivity of our GC. So how do we do this? We have a look at the analytes of interest, aim of the analysis and application, GC configuration, GC column phase, and the sample mixture. So when we think of the analytes of interest, we need to establish what they are. We need to check if they're suitable for GC, and what are the physiochemical properties and how they'll influence the GC parameters. So when we're looking at GC and HPLC suitable analytes of interest, we want to make sure that we're going in the right direction. For GC, we want low boiling point below 400 degrees, easily vaporized, low molecular weight. We want the stability at high temperature, high vapor pressure, and organic compounds. So what about essential oils? Do they fit in well for GC? That we can see that the essential oils have a low boiling point between 100 and 200 degrees, easily vaporized, molecular weight is usually below 500 Daltons, thermally stable, decompose just above 400 degrees, high vapor pressure, organic compounds, and then soluble in a liquid phase. And I highlighted in purple that on the GC side, they hit all the main points. So these are going to be perfect candidates to be analysed with GC. But we can still use them with HPLC. It's just that we're going to get better results when we use GC. So it's always good to double check this with each of your analytes. Physiochemical properties of analytes influences the method direction, so the choices made with the products. So the polarity can influence the column phase selection, the boiling point can influence the inlet temperature and the oven temperature. Similar or different boiling points analytes can influence the column phase selection. Structural isomers, if you want to separate them, you may need mid to high polarity phase columns. If the sample is non-labile or labile compounds need softer conditions, lower initial temperatures. Then if the sample matrix is clean or dirty, this can be a point that influences column dimensions, line of choice, and sample prep process. So then when we have a look at the aim of the analysis or the application type, what are we trying to achieve in the analysis? What application notes actually suit what you're trying to achieve? And are there any application-specific columns available out there? When we look at the aim of analysis and application, what is the information required from the results? So these are the sorts of questions we need to be looking into. So is this a new or established method? Is the analysis of a simple or complex sample? Do all analytes need to be detected and separated? Do we require high level or low level resolution? Are application notes available for this aim of analysis? And what level of sensitivity is required? And we want to look at these questions because not every run or injection needs to have amazing resolution, and not every sample is the same. For example, this Orachlor 1254 PCP mixture has been analysed on a high chrome, high Se54 phase, and there's not great resolution, but that's all we need. We want to see a few peaks, a few hits on those analytes, and that works for that application type. You can see we're having a look at cyclic hydrocarbons using the high 1 phase, and we can see really great resolution. We can see a distinctive separation at the baseline, and we're having a look at these 4 analytes, and maybe we need to see this high resolution. So not every analysis type is going to be the same, not every application is going to fall into the same umbrella, so we really need to just double check this because this drives the type of method we're going to be developing, the products that are going to be suitable, and then if your GC configuration is suitable as well. So with the aim of analysis and the application, there's lots of resources to hand. So the first one is the Avantor GC phase document and the cross-reference document. On the GC phase document, you can see important parameters like maximum temperature of the column, composition of the phase type, application areas, whether it's general purpose column, what type of analyte it's best to analyze, if it's a specific application related column, and then also the methods, EPA method numbers, and the USP type of the phase. You can also check the application notes in our application library online, and here you can search, you can have a look at the column type, you can search specific analytes of interest, and it just gives you more of an idea to see what trends of columns are out there and what they're being used for. You can also check the monographs of the analyte, and are similar monographs of interest in USP databases, and you can contrast and compare the other types of columns within that USP phase. When looking at the GC configuration, you need to check what type of gases, inlet, detector, samplers you're using, and then also what is the GC type, just to check its limitations and heating, etc. And then, is the configuration suitable for the analysis? So when we look at the GC configuration in relation to carrier gases, you may not have much of a choice if you've got a GC that's already set up with a gas. But here's some information that's very helpful. So nitrogen was originally used with packed GC columns. It can still be used today, but it's got a very slow retention time. It's the second most viscous out of all of these three gases. It's got low diffusivity. Helium is the most popular, but it is the most viscous of all three and has a higher diffusivity than nitrogen. Hydrogen is the most efficient carrier gas, least viscous, and has the highest diffusivity of all three gases. And viscosity and diffusivity affect the speed and the pressure. So these qualities are important. So why does the carrier gas, linear velocity, the speed the gas travels in centimetres per second, why does that matter? So the faster the speed, the faster the retention time. So when we look at this diagram on screen, the Van Dienster equation, we can see we've got nitrogen in the blue, and that has an optimum velocity of 10 to 15 centimetres per second. Helium has a bit faster, 25 to 35, and then hydrogen at 40 to 50. And this means when it gets past this optimum velocity, the chromatography then starts to deteriorate. The efficiency of the column gets worse, and that's what we don't want. And this is measured in a HETP value. And this is a theoretical way to measure column efficiency. So the lower this value, the better. And the faster the gas travels, then the shorter the retention time. But we don't want it too fast, because then we lose that column efficiency, we lose good chromatography, we start to see band broadening, and that's what we don't want. And as nitrogen, as you can see on here, only has a narrow range, when we look at helium and hydrogen, they have much broader ranges. So they can go much faster before we see that HETP value increase, and then we lose the column efficiency and we see peaks broadening and worse chromatography. So hydrogen is the best choice because it can go much faster before that HETP value rises, and then it doesn't even rise quite sharply compared to the nitrogen. So this is why we want to try and move towards hydrogen, because then we can get faster retention times without having to fully sacrifice on the chromatography. An example is when we have too high of a carrier gas linear velocity, we have really, really fast retention times but less resolution. Then when it's too slow, we have a long retention time but more resolution. So the wider this range, this optimum carrier gas linear velocity is, the more flexibility we have with decreasing the retention time and then still maintaining a decent level of resolution. So then when we're looking at the GC configuration, we have inlet and detector limits. So understanding which inlet and which detector you have is really important to help and see what you're capable of achieving with your method. So if you look at the splitless inlet, this is a general use and one of the most popular inlets that is installed with the GC. But if you wanted to run at really, really low temperatures and keep the sample very cool when it's introduced into the inlet, you're not going to be able to do this with a splitless because it doesn't have the cooling capabilities. But the MMI and the PTV, these inlets do have cryo cooling and cooling mechanisms. So this is where it restricts you a little bit in your method, and just making sure that you're looking at the right applications that fit your configuration of inlet. And that same goes for the detector as well. So we have an FID, and this is a general use detector, and so is the mass spec. But they're two very different detectors and they're very different methods. So we do need to be very aware of that. Then there are very specific detectors, so like the sulfur chemiluminescence detector and the electron capture detector. Sometimes these can be very specific to certain functional groups that they can detect. So understanding this gives you much more advantage over selecting a suitable method and application that you can use on the GC. So a good way of understanding this is to look at the inlet types, and if we just compare two of them. So we've got split list and the PTV, the programmable temperature vaporization inlet. And with the split list, when we look at the suitable sample type, this is a default standard inlet, and you can do hot injections, non-labile samples. But then when you look at the sample type for PTV, it's cold injections with rep and cooling. You can look at a wide boiling point range, but the samples are labile and they're more suitable for PTV. Sample concentration for both of them can be high or low. Then when we look at the suitable injection mode for each of the high or low concentrations, there's, for high concentrations, split and purge split. And then with the PTV, you can see there's an additional option for solvent vent. And then for low concentration samples, a lot of the time it's a splitless injection. So when we're looking at the liner types for the splitless and PTV inlets, you can see that there's straight liners, straight cyclo, gooseneck or double gooseneck. We've got then PTV or MMI specific liners that are baffled and dimpled. So for each inlet, and then for a lot of injection modes and injection types, and then types of samples, liners are different. So this is why understanding the type of inlet you have then leads you to understand the type of samples you can introduce. And then the other variations you need, maybe you need quartz wool, maybe you don't, maybe you need the gooseneck because you're doing splitless injection. So this is where the variables can come into play, and then understanding your vapor volume as well. So you're ordering the correct type of liner and the correct size. Column phase. So what column phase will retain and separate the analytes to fit the desired results? So what phases are going to work for your so what you're trying to achieve? What dimensions are also going to be suitable for your sample? Very important point to consider. So stationary phase for GC columns is a liquid coating of polysiloxanes or polyethylene glycol with various substituent groups. We've got the two extremes on screen, so we've got non-polar and polar column phases. So we've got 100% dimethyl polysiloxane. Then we've got PEG, polyethylene glycol or wax columns. Then, to increase the polarity, the polysiloxane phase and methyl groups are replaced with phenyls, cyanopropyls, or other groups. And you can see the differing percentages. So as more of these methyl groups are replaced, or we move into the PEG phase, then the polarity increases, and there are additional mechanisms of separation as the polarity increases with these additional groups that are incorporated into the stationary phase. So this means when we have the lower polarity or non-polar phases, these separate based on the boiling points. So boiling point influences the elution order, whereas the polar phases, the phase interaction influences the elution order. So you can inject the same sample on two different polarity of phases, and you may see a different elution order. And you can see the range of columns. This isn't all of the columns that we can offer, but it's the majority of them. And you can see how the polarity goes from low / non-polar phases and all the way up to high polarity. And you can see this influence a lot more. So when we have a look at some chromatograms, so for a non-polar column, the high 1 column, we had a look at some cyclic hydrocarbons. And you can see the analytes of interest on the left-hand side, and you can see them in boiling point order, and they have eluted in this order as well. So the higher the boiling point, the larger the compound, and then the higher the retention, and they elute last with the higher boiling point. But then this compared to a high acid FSAP phase, which is in higher polarity. The elution order is influenced by polarity and interactions. So we can see on the right the list of analytes. So we've got acetic anhydride with a boiling point of 139.5 degrees. And then acetic acid actually has a lower boiling point, but it's eluted after the acetic anhydride, and that's because the boiling point does not define when the analyte elutes out of the column. There are more mechanisms, so there's more retention when it comes to polar phases, and then more difference in the interactions for the analytes with that phase. When you have a look at column dimension considerations, it can seem quite overwhelming and there's too many choices, but if you break it down, you just need to ask yourself, what do I need to get out of this column? So let's have a look at length first. So I've highlighted medium, so these are the most common lengths, 20 to 30 meters. Usually you have analytes which have a broad range of boiling points, and then you're looking at medium resolution. You don't necessarily need really high resolution, maybe just standard GC analysis, moderate retention time, maybe like above 20 minutes. It's going to be a medium cost, and then there's more length on the column as well. So if you're doing lots of trimming and lots of maintenance on the column, you're not going to lose much length that's going to affect your analysis. And then medium complexity of samples, and you can use it with GCMS. Then on either side, with short or longer columns, they become more specific and more application motivated. So the longer columns tend to be for low boilers, very complex samples. There's very long retention times, but for that application, that's okay. It works well for those analytes. The issue is that cost is higher because when you have more silica, more phase, it costs more money. Then with shorter columns, this tends to be for lower resolution, short retention times, less cost. Fast GC using GCMS, and there's only a few compounds in the sample maybe. So this is how you make your decisions or direct your decisions when you're looking at the length. Looking at the ID, let's look at the larger end of the IDs. So we've got 0.4 to 0.53 millimeters ID. So these tend to be for high flow methods, higher capacity of samples. So you've got maybe 2,000 nanograms of sample, and this is based on a column that has a film thickness of 0.25 microns. And then this method that you'd fit with a larger ID tends to be splitless. You've maybe got a headspace on there. You're just dealing with a lot more coming into the column, but that's okay because the column is wide enough to handle that, and that works for the application. Whereas if you're looking at the other smaller IDs, and they tend to be for lower flows, lower sample capacity, and you may be just looking at different types of samples, maybe more complex samples that need to be in a smaller space so they can have more interactions with the phase. So then looking at the film thickness, we'll look closer at the thin film thickness. So this gives decreased retention and shorter retention times, lower sample capacity, works good with higher temperatures, less column bleed because there's less fade, medium to high molecular weight compounds. So then if you're looking for a more retentive method, or you having volatiles that are in the sample, low molecular weight compounds, the thicker film thickness is going to be more suitable compared to the thin film thickness. This is how you direct your decisions on the type of film thickness that you may need. Sample mixture, double checking that you know exactly what's in the sample mixture. Is there a sample prep protocol that's ready to go? Is the sample solvent / diluent compatible with the column? So the sample mixture, when we're looking at the solvent and diluent, when we're having low polarity samples introduced onto a column, and the column is also low polarity as well, we tend to want to stay with low polarity solvents. And the same goes for polar analytes and polar columns. We want to stay with polar solvents, because if we're injecting the complete opposite polarity of solvent, then this might have issues with the phase. It might cause damage to the phase, and we don't really want that. We don't want like solvent mismatches or anything like that. So we need to make sure that we're picking suitable solvents. If you've got a mixture of polarities in your sample mixture, or you're looking at using mid-polarity columns, then you can use an intermediate polarity solvent as a compromise, so maybe ethyl acetate. So these are a few things that you need to consider, and this is where, again, application notes are very helpful. Other considerations are sample types and detectors need to be considered because they have limitations and may need more considerations when it comes to the solvents that can be used. And also, when you're doing standard GC injections, the solvent needs a lower boiling point than the compounds of the sample mixture. So then, when we've established all of these points, then we're good to go with the method development. And when we develop the method, we have a set of goals and we want to achieve when we optimize parameters. So we want to transfer 1, enough sample onto the column for detection. 2, we want to see all the peak solute. 3, we want to reduce the retention time as much as possible without sacrificing the chromatography. 4, we want to see good peak shape and resolution of the peaks. 5, we want to see a good response to enable concentration calibration after the method development has been done. And then 6, we want to achieve reproducible results. And then once we've achieved all of these points, once the retention time is reduced, resolution is good, all the peaks are we've got decent responses, then we can run further injections to test reproducibility. So we start off with doing a scout run. There's 2 approaches. First approach is when we use a lot of the application note method parameters, and then the second is when we set up a method using the default method in the software, or we can enter the parameters manually. So with the first approach, we want to acquire a suitable test mix or external standard. We want to have the application note available, and then we can use all the parameters in the method as applicable, adjust any parameters as needed for the GC configuration, and then run an injection and assess the results. Then, after you've assessed that first run, then you can set up more runs with adjusted parameters. So usually you'd start with 1 parameter and work through that. So, for example, the oven ramp. You can do a few different settings. So you can do 20 degrees on 1 injection, then 30, 40, 50 degrees per minute. Run those injections, select the best oven ramp, and then you can move on to a different parameter and run more injections and repeat. And we try to change it parameter by parameter if possible. Then with the second approach, we again acquire the suitable test mix. We set up the method, and we tend to recommend to try and start with a default method, or you can do checkout methods. And then this is just a bit easier because a lot of the settings that you want to start with and then do the method development may already be loaded for that inlet and detector type. Then adjust the parameters to suit the GC configuration as needed. Do the same again. Run an injection, and then you can set up more runs with changing it parameter by parameter and then selecting the best out of that run set. And then optimize and set up more runs parameter by parameter. The main thing to do is to avoid changing everything at once. If we change everything at once, it's very easy to lose track of which parameter is maybe causing the problems in your peaks and your chromatography, or maybe the parameter that you changed that maybe has improved the chromatography. So then when we look at a split injection, so we can develop this method. So we're going to be working with, in this example, 0.32 millimeter ID and 25 meter length column. We'll be using a splitless inlet in split injection. The column capacity, and you can check this online in general on chromatography websites, and they're very helpful, but just double checking if you're not sure of the column capacity. So this one has a column capacity of 50 to 150 nanograms per analyte, and we tend to use the higher end of this capacity and then reduce it, dilute it. Injection volume could be 1 microliter, and then a lot of the settings are usually set up in the default method or as standard, but in inlet temperatures, 250 degrees is usually standard. Column flow, 1 mil a minute. You would check the flow rate, the range for that column dimension. You'd see if it was too high, the column flow, then you get overpressure, so then you just reduce it. Column flow mode, it's best to stick with constant flow, because if you select constant pressure, then you're not going to be hitting that 1 mil a minute. It will be adjusting for a constant pressure, which is not really what we want. Start with the split ratio of 50:1 in this example. Sometimes you can start as low as 10:1, but with this example, we're going to start with 50:1. Initial temperature tends to be 40 degrees. We don't have a hold time for split injections unless it's in the application note. Oven ramp is 10 degrees per minute. Final temperature of the oven, we tend to go for the maximum temperature of the column if needed, then minus 10 to 20 degrees. You don't want to exceed that maximum column temperature. And then the final hold time, just as a start, is 10 minutes. And this allows all the analytes from the sample to elute. So then let's just remind ourselves of GC inlet split injection. And you can see that the arrow showed the direction of the flow. So it's going out the septum purge and then down the column and then out that split vent. And the split vent is open throughout the injection. The sample is introduced, it's vaporized, and then the majority of the sample goes out that split vent, and some of the sample goes down the column for separation and detection. This method of injection, this mode, is used when the concentration of the sample is high, and we don't want all of it going down into the column. So we're going to look at what we can adjust. So first we're going to look at the flows and the inlet settings. So if we just go straight down to the inlet temperature first, we don't necessarily need to adjust this. We only need to change it if we're seeing degradation or real issues with the peaks not really coming through very well. If we do need to adjust it, maybe we can increase the temperature by plus 25 degrees steps up to 300, but only if it's needed. Column flow, you can increase this by 0.2 mil per minute or increase the linear velocity by 5 centimeters per second steps. This is only if you're getting a really low response. Maybe there's not enough flow coming through to the column. Be it in constant flow or constant velocity, we don't really want to change this. The main thing to change is the split ratio. So you can set split ratios of 1 to 75, 1 to 100, 1 to 150, and 1 to 200. You can even go higher if needed. Ensure enough sample is being transferred to the column. So then when we go back up to column capacity and injection volume, if we have a look at injection volume, if you see an overload of the sample and increasing the split flow isn't helping, then dilute the sample. If you're getting a really low response, then you can increase the sample volume that's injected. If the split flow doesn't help, again, by decreasing the split flow. But we need to make sure we're not overloading the inlet with too much volume because we don't want to cause a backflash. And that's when there's too much basically vapor that's inside the inlet. But then if this doesn't help with the enough detection of the analytes and we need more sample or less sample, then you can adjust the concentration by plus or minus 50 nanograms as needed. But first, just adjust the split ratio, adjust the injection volume first and see if these help. So when we have a look at optimizing then the oven ramp and the temperatures, we have an initial temperature of 40. We can actually calculate the initial oven temperature of the first eluting peak and then minus 45 degrees. That's a really good place to start. And obviously then you can optimize as needed. The initial oven time, hold time, we don't have one for split injection, but you can add hold times over maybe analytes that are mid-eluters and maybe the co-eluting. You can add little holds over those peaks just to give them a bit more time at that temperature to separate from each other. Oven ramp, so then you can have a look at the optimum oven ramp by calculating 10 degrees per the T0 time. Or you can do it in steps of plus 20 degrees, 30 degrees, 40 degrees, and 50 degrees per minute, and then just run those injections at those different settings, and then just see which one is the best, where all your peaks are eluting in a decent amount of time and resolved well. Final temperature, so you check the final temperature of the last eluting analyte, and then you can plus 20 degrees on that temperature, and as long as you're not exceeding the maximum temperature of the column, this is suitable. And then for your final hold, you can either remove it completely if you don't need it. This is just to make sure all the analytes are eluting and you've got nothing left over. So you can adjust this as needed. You can just reduce it, remove it, do whatever's necessary. There is a difference when it comes to splitless injection, and this is why in this section on the right that I've highlighted. Splitless is very different in oven parameters. It has an initial temperature that is 20 degrees below the boiling point of the solvent, or as low as possible the inlet will allow. This allows for solvent focusing and cold trapping, which is essentially concentrating and focusing the sample and the solvent at the head of the column, which is different from the split injection. So the first few settings are the same: column capacity, injection volume, inlet temperature, and the flows. But we have this splitless hold time. The standard default is 1 minute, but we've got up to 2 minutes of a splitless hold time, and this is just the time it takes to do the injection for all of the samples to be transferred to the column. The splitless purge flow is just the common default of 50 ml a minute. This just clears out the inlet after the injection is complete. Then the initial temperature is 20 degrees below the boiling point of the solvent. Initial hold time of the oven, we didn't have it with split, but it just matches the splitless hold time in this splitless mode injection. And then the oven temperatures are adjusted as they were in the previous slide for split injection. Let's just have a look at a splitless injection and how it's different from split. So this time we've got that split vent is closed throughout the injection, and it is opened after the hold time. The sample is injected as usual and vaporized. Then all or as much as possible of the sample is transferred to the column. Then at the end of the hold time, that split vent is opened and any residual solvent is then vented out. And this is usually in low concentration samples, and we've got up to 2 minutes of the hold time to transfer the sample, but we do want to optimize it because having it too long or too short does cause issues. So then the main areas to adjust in the splitless injection is to adjust the splitless hold time. So we need to adjust it so it's ideally 1.5 to 2 times volume of carrier gas sweeping of the total inlet. And we've got up to 2 minutes of hold time we can use. So this takes a lot more optimization, a little bit more understanding of a splitless injection. So this takes more time and it is a bit tedious, but it's definitely worth it if you can invest time in this. Then if you need to optimize the purge flow, this is usually as a last resort if you've got carry over, but you can adjust it by plus 10 ml per minute. Then the other areas to optimize, same again, the oven ramp rate, the final temperature and the hold time as it was for split injection. And then we just need to have a look at the initial temperature when it's a splitless injection. So this is important. So if we've got peaks widening, then we need to reduce that initial temperature, reassess after we've done another run, see how it looks. And we also need to just make sure that if we need temperatures that are much lower, maybe that splitless inlet isn't capable, and we just need to be really honest and when we're having a look at these methods if the inlet is suitable for the method that we're working with. And then the initial hold time, and this just matches the splitless hold time, the time it takes to run the injection. You can still add that hold for the mid-eluters if needed, if they are co-eluting. So now we're on to the FastGC section. So what is FastGC? So this is a technique that allows you to reduce the analysis time while keeping an adequate resolution power, thus increasing your throughput. It can be applied to medium to high complexity mixture analysis and provides 3 to 10 times faster analysis compared to conventional GC. So what is required to achieve FastGC? So first of all, we need to reduce the retention time. So the length needs to be shorter, 5 to 10 meters of the column. High temperature ramp, so we need to have it at 15 degrees per minute or more. And then we need a higher gas linear velocity. And we discussed this earlier in the presentation, how hydrogen is much more suitable for FastGC as we can increase the carrier gas linear velocity without sacrificing the column efficiency and the results of the chromatography. We need to accommodate for the faster speeds and retention time by increasing the resolution. So this is where we use hydrogen because we don't lose out on the resolution as much when we use hydrogen, whereas we can see on helium the column efficiency deteriorates much quicker. The ID of the column needs to be smaller, usually below 0.1 millimeter ID. Thinner film thickness 0.05 to 0.2 micron. We also require fast acquisition rates of at least 50 hertz. It's good to check that the GC is suitable for this. Additional information, old MS systems may not be able to handle hydrogen as a carrier gas, so it's good to just double check this. Just another consideration, the Agilent Intuvo 9000 GC instrument is a fast GC instrument and it has its own specialized columns. Avantor do not supply these Intuvo 9000 fast GC columns. They are in a completely different format, these fast GC columns for the Intuvo instrument compared to the majority of other GC capillary columns. And you can see the difference, and the standard or fast GC capillary columns that are sold elsewhere and at Avantor are usually on a round bracket that slots into a GC oven and on a little hanger, whereas the Intuvo 9000 GC columns are very different and they're not compatible with standard GC instruments with standard ovens. So this is just the point that you can't buy an Avantor capillary GC column and then fit it into an Intuvo instrument. It's just an important point to make, and this is why when you're looking into columns, just to make sure you send the information that includes the GC type. So then we're going to have a look at transferring from a standard to fast GC method. So a shorter column will show a faster retention time without changing anything, without changing any parameters, but the method would need to be optimized because the resolution may be poor, and you do need to optimize it because having a shorter column isn't the only thing you need to achieve fast GC. We'll look at adjusting the following parameters, so increasing the carrier gas linear velocity, adjusting the inlet flows to make sure enough sample is being transferred to the column, and adapting the oven ramp rate to accommodate for all of the above. And you can see on the standard method we've got 30 meter column, 0.25 millimeter ID, and we've got a slightly thicker film thickness as the data I had to use just wasn't with a really thin film thickness. The carrier gas is helium. Linear gas velocity is 42 centimeters per second. Column flow 2 mil per minute using constant flow, ratio of 1 to 10. And then the rest of the parameters are pretty standard. Besides, the final temperature is 270 degrees, so a little bit lower than usual. And the runtime overall is 25 minutes. So let's see how we can reduce this. So when we increase the carrier gas linear velocity, this decreases the retention time. So we can start off, this is a way you can just develop the method and run some tests. So you can start from 40 centimeters per second, and then you can plus or minus 10 centimeters per second steps. Maybe you can go to 50, 60 centimeters per second, maybe more. And then you can have a look at which one looks best. You should see the retention time reduced by at least a few minutes, up to half the original retention time. And this is a way to know that it's going in the right direction. If you're seeing that drop in retention time, then that's the first step of achieving the fast GC. And again, this is just a reminder of the optimum gas linear velocities, and this is why hydrogen is very helpful, because we can go to those higher linear velocities. So then when we've transferred to this fast GC method, in this case, we have moved from helium to hydrogen. You may not be able to do that at the moment, just because you may have a gas setup and that's the gas that you're going to use. But ideally, we want you to use hydrogen. Helium is much more difficult to optimize because it's more viscous, and you can't go up to these higher linear velocities. So in this fast GC method, we're at 80 centimeters per second. The column flow has reduced because we've got smaller dimensions, and we have to stick to the limits of the column as well, because each dimension will have different flow rates that we can use in a range, within a range, and you'll get overpressures if you go too high with your flows. And then with the flow mode, again, we want to stick with constant flow or constant velocity. It depends on your software if it has constant velocity, but ideally we want to go for constant flow. Then we adjust the inlet flows to make sure there is enough sample being transferred to the column. So the higher the velocity, this can increase the flow rate and split flow if we're not adjusting the method for the smaller dimensions. So this is where we need to be making sure that we're reducing the flow rates, so we're not overpressuring the GC. And you'll see issues with the peaks if these flows are not optimal. So if you have poor peak shape and if there's overload, then the split ratio is too low and you need to increase it. So less of the sample is going down the column. It's just too much and it's saturating the column. If you've got poor response and you're losing peaks, and the split ratio is too high and too much sample is going out the split vent, then you need to decrease it. So you can plus or minus by 20 to 40 on that split ratio. But when you are using these lower dimensions, these smaller dimensions, the minimum split ratio is 1 to 100, up to 1 to 400. So you want 10 times less sample concentration going down that column compared to standard GC. So here's just an example of what you can do just to start off with. You can start with 1 to 100 and then increase as needed. And then you adapt the oven ramp rate. So you can plus the oven ramp rate by 10 degrees, 20, 30, 40, 50. You can even go higher if the GC is capable. And then you can see which of the oven ramp rates works the best and helps reduce that retention time even more, and then resolve the peaks as best as possible. You can calculate the optimum ramp rate by having a look at the T0 time, and then it's 10 degrees per the T0 time. There's further calculations that you can do for the oven ramp rate and isothermal temperatures. So this is the set of calculations that you could do to have a look at. One, the oven ramp rate that's going to be more suitable, taking the original conditions and then comparing them to the new ones. And then you can do this with the isothermal hold times as well. So you can check this online. So these are just calculations for the oven ramp rate and the isothermal hold time. I won't have time to go into them in great detail today, but it's just the awareness that you can use these to help craft the GC fast GC method from a standard GC method. And then you can see the initial temperature. So this is much higher as with fast GC because we're looking at high boilers. We're not going to be starting at those necessarily lower temperatures, so we can increase the temperature much higher to start off with, and then this further reduces the retention time. And we don't have a hold time on this method. The oven ramp rate has been increased to 30 degrees per minute, but it could be increased much better. It just depends what works best for the method and for the chromatography. And then we've adjusted the final hold time and reduced it down to 1 minute. And then you can see, and now we can see the new retention time is 6 minutes. It's massively shorter, it's faster than 25 minutes. So this is just the retention time, but then you can go on to then optimize to make sure that resolution is still good as well. So then when we look at the comparison of standard and FastGC for chamomile analysis, we can see the run has been reduced from 55 minutes to 10 minutes. Main parameters we'll be focusing on are the oven ramp rate, which is 3 degrees per minute, the carrier gas flow at 1.5 milliminute, injection volume 1 microliter, split ratio 1:50, and then the column details, it's a standard column with standard dimensions. So let's have a look at when we change these parameters in the column to FastGC, how it influences the retention time. And then when you see the reduced run time from 55 minutes to 10 minutes, what was changed? So the ramp rate, the oven ramp rate was changed to 50 degrees per minute from 3 degrees. We've got a lower carrier gas flow at 0.5 mil per minute. We've got decreased sample injection of 0.5 microliter, higher split ratio at 250, and then you can see the dimensions are massively reduced for the column that was used. So this just shows the difference, and we could go even faster with that method by increasing the carrier gas linear velocity, but then we might lose some of the resolution. So the main thing is to try and find the right balance where we've got fast retention time but decent resolution. So then when we look at how do we actually select the column dimensions when we're going from standard GC to FastGC. So we use the phase ratio, and this is a value that characterizes the film thickness and the column internal diameter combination and how retentive that combination is. So the lower B values, and these have increased retention. So these we for like low boilers and analytes that need more retention. So these combinations are better for those. And then the higher B values, you can see them on the far left side, these have decreased retention. So the analytes fly through much faster. So the phase ratio is helpful. It helps you choose a column with a similar phase ratio. So when you're changing down to a smaller dimension or higher dimension, that you're keeping a similar amount of retentiveness. So you're not seeing a massive change in the chromatography. You just see maybe a differentiation in the retention time. So then when you have the blue highlighted values, these are below 100 for highly volatile, low molecular weight analytes, and then up to 400 and above, these can be medium to high molecular weight analytes. And here you can see the calculation that you can do, the formula to double check the phase ratio. So it's the column ID in micron divided by 4 times film thickness in micron. And I double check this with the film thickness of 0.18 and the column ID of 0.25, just to check if this calculation worked well. And it does, so I achieved the same value and the phase ratio of 347.22. So then this is a good way if you want to double check if you haven't necessarily got an idea of where your current dimensions fall into this table, you can do this calculation. So to summarize, we want smaller column dimensions and sample dilution, faster oven ramp rate, and higher carrier gas linear velocity to achieve FastGC. So thank you very much for your attention. I hope this was really informative and helpful. And if there's any questions, then please let us know. Thank you.
Thank you, Kirsty, for a great presentation. We have a few minutes left for questions, and Tony Edge will be answering your questions today. Just a reminder to our audience, if you want to submit a question, you can do so in the Q&A box at the bottom of your screen. And any questions that we are not able to get to today will be answered by email after the presentation. Okay, let's get to our first questions here. Can you describe a strategy for selecting an effective internal standard, looking at things such as retention times, boiling points, molecular structure, concentration per detector response, etc., when compared to the analytes of interest?
Yes, so that's a really good question. When we're looking at internal standards, the internal standard should mimic as much as possible the analyte of interest. And so for that, we would ideally look for a stabilizer type label. That isn't always feasible, in which case we then have to have a look at the other physical parameters, the physiochemical parameters of the molecule that we're actually analyzing, the analyte. And for this, I would look at initially retention time to make sure we've got retention time, and that should be associated if we're looking at a non-polar column at the boiling point. But we can also have a look at compounds that have a very similar structure, and that would be the route forward. I think ideally a stable isotope label, but failing that, something that has a similar retention time, because that would then undergo similar physical process within the column. And so any differences that you might see because of it eliciting at different retention times would be eradicated. So that would be my suggestion for that one. But good question, thank you.
Thank you. Next question, when would a standard GC method be more appropriate over a fast GC method?
So this is an interesting one because the trivial response is that why would you want to go slower? But actually, when we look at this in more detail, we need to consider the physical constraints that we have with the system as well. So my suggestion here would be that in terms of the methodology, if the system is optimized in terms of fast GC, then absolutely the fast GC should always be used. Where a system hasn't been optimized in terms of thermal gradients, etc., then in that scenario, then standard GC. And this also relates to detector responses, etc., as well, detector response times as well. Hopefully that answers the question for there. Thank you.
Okay. Next up, it may sound irrelevant, but what kind of column do you recommend for propane and methane analysis, and what criteria do we need to pay attention to?
So when we're looking, and this is not irrelevant, so when we're looking at permanent gases, we need to be very aware of the retention. And so ideally we want a non-polar column. And so something with, I think, as Kirsty was alluding to in the presentation, the polarity starts off with 100% polymethoxysilane. So if we're looking at that, that may give us a starting point. In terms of the other characteristics of the column, then the film thickness will also give us a good indication of retention. And so a thicker film thickness will also be a good suggestion there. So instead of perhaps using a 0.1, we might want to use a 2.5 or even a 10 to get a decent retention time on that one. So that would be my initial suggestions. And then for the individuals that have access to packed columns, then that might be an interesting approach as well. But certainly looking at film thickness would be something that I would look at initially, and then making sure that you have a thick film column. Or failing that, look at moving on to a packed sorbent or zeolite of some description, which may give you better retention because of the enhanced surface area. Okay,
great. Next question. When we are considering concentrations to decide between split and splitless injections, are we focusing on concentrations of anything to avoid damaging the column, or only focusing on the concentration of interest?
So this one, we need to be really looking at the total amount of components that are actually going onto the column. In terms of what will be damaging the column, for that we're really looking at, I guess, aqueous components and trying to avoid those aqueous components on the whole. So in terms of the loadability and making sure that we don't overload the column, then absolutely it's the total amount of analyte or compounds that are going onto the column that is the biggest consideration. That helps.
Okay. Can you please repeat why you would not need a hold time for temperature when using the split mode?
So in the split mode, part of the injection solvent, or part of the, not the injection solvent, the sample goes directly to split straight off. So any of your components that are going to be removed will get removed instantaneously. And so in therefore having a hold time, it's not so critical, because in essence we are just looking at moving the analytes directly on, and we're not holding them in that injector area for a period of time. So in split mode, all of the components are able to go down the split if they want to, and that will be based on boiling points, it will be based on differential boiling points, and it will be based on the flow kinetics going into the injector. And the remaining elements, components, should I say, then go onto the GC column. So having a hold time there doesn't influence the injection so much. Where we're looking at a split-less injection, and there we're having the components being held in that injector for longer because the split valve isn't open. There it becomes much more important that we do have a hold time so that we get a good movement of our compounds onto the start of the column.
Okay. Next up, what types of columns do you recommend for FAME analysis, especially trans fatty acids?
So if we're looking at fatty acid methyl esters, the typical type of columns that you might want to use for that would be a PEG or a free fatty acid phase column. And again, as Kirsty sort of demonstrated, those would be available on that spectrum of columns. So hopefully, yeah, so those would be the columns I would recommend.
Okay. Is a good linear range for quantitation expected in headspace GCMS? Is a stable isotope internal standard necessary? So if you can use a stable isotope, then I would always recommend it for quantification, absolutely. I think if you're looking at getting linearity, then there should be no reason why you can't get linearity over a range. Obviously, in terms of linearity, it will depend on the kinetics of the diffusion of the compound into and out of the headspace. And that will be dependent on a variety of different factors relating to the individual analytes that you're looking at. So I think in that scenario, the linearity range will depend in terms of the kinetics of the diffusion of the analytes into and out of the headspace. And obviously, there will also be the detect linear range. Hopefully that helps with that one. Okay. Next question. Is the fast GC method reasonable than the HPLC? I think that perhaps mean more reasonable than the HPLC for small molecules and biological specimens. Again, that sort of, in terms of the choice of the different approaches, whether you use HPLC or GC, that really relates to the volatility of the compound. Now, there is a degree of overlap, and so you can have some compounds that would be applicable for GC and also HPLC. In that scenario, both would be applicable, if you like. However, I think it really then comes down to the other criteria of do you have the instrumentation available? Do you have the knowledge in order to use it? So my preference, I must admit, would be BLC.
but if your preference is to use gas chromatography and you've already set up for that, then gas chromatography. But I have to stress, in terms of the choice of the original technique, whether it's GC, let alone fast GC, or HPLC, it really relates to those first couple of slides that Kirsty went through, describing the range of molecular masses that are applicable and also the volatility. And it's really the volatility that should drive it. There is a degree of overlap, and there are certain compounds that can be analyzed in GC and also LC. And for that one, this is a GC seminar, so perhaps I should say GC, but I think it comes down to a personal preference. I don't think in terms of the range of selectivity and resolution, if you've got GC, then it may be better for GC for certain compounds. It may be better for LC in certain compounds. And again, some of that will come down to looking at the resolution that you can get and the selectivity differences you can get. And it may be that with LC you get better selectivity differences, but with GC you get better efficiency. And the combination of selectivity and efficiency gives you a resolution. How well can I separate my components? So there needs to be consideration of what skill sets are available, what equipment do you have, and then also what is the selectivity and the efficiency that you get from both techniques. And if you're looking at in terms of efficiency and selectivity, that will be very dependent on the compound and the columns that you're using. So apologies, that doesn't quite answer the question, but hopefully it gives you enough information to make an informed choice.
Okay. Time for just one more question. I'm running a same analysis with an FFAP column, 30 meters, 0.53 micrometers. Compounds are methyl esters of C16, C18 to 0, C18 to 1, C18 to 2, C18 to 3. I just learned that the solvent should be close in polarity to the analyte, but I have been using hexane. Should I switch, and what would be a good choice?
Hexane is absolutely fine. This comes down to what is the injection solvent actually doing, and the rationale for the polarity really is the solubility issue. So, however, the compound needs to get dissolved into the solution that you're injecting. The other aspect of the injection solvent is that you want it to volatilize really quickly, and it should be having a much lower boiling point than the analytes of interest. So looking at those two considerations, hexane is absolutely ideal for your fatty acid methyl esters. Yes, if you can get a low boiling point compound that's got similar polarity, that may help in terms of dissolving up more of the thames. But I think in this scenario, your hexane will be dissolving those fatty acid methyl esters in an admirable way. So there's no issue there at all. Hexane is a good choice for injection solvent in that scenario.
Okay, terrific. Thank you. That is all the time we have. Thank you again, Kirsty and Tony, for your fascinating presentations. And thank you to our participants for being a great audience, and On24 for technology and production services. And thank you, MacMod Analytical, for the sponsorship that made this interactive webcast possible. Be sure to check CNEN or CNEN Online for information on upcoming webinars. For CNEN Webinars, I'm Catherine Dold. Goodbye.